Okay, so now we're going to switch to our online talks. And the first one is Gianluca Bez, as I mentioned. And let's see. Oh, he's all ready to go here. Let me get this up and maximized. And you're ready to present. Can you share?
Okay, so I'm gonna go ahead and get started. So my name is Gianluca Bez. I'm a research scientist at Lawrence Berkeley National Lab, and I'm gonna share a little bit about the work that applications, high-level library, parallel middleware. So you can think of the MPIO there, low-level libraries, the forwarding layer if you have one on your system, and the parallel file system until you finally reach the storage hardware. So using this entire stack efficiently is a very tricky and complex problem. There's a lot of interplay between the factors that can affect performance. So you may change something in one layer, and that might bring the performance back down on another layer, and so forth and so on. So trying to determine the best set of parameters that you can use, or what is actually affecting your application's performance based on what you were expecting is very hard to guess sometimes. There are always various optimization techniques that have been developed by the community over the last years that kind of expose a lot of tunable parameters where we can switch parameters in different levels of the stack, sometimes in a high-level library like HTML5, sometimes we have parameters on MPIO, on the file system like stripe size and count that was mentioned in the previous talk. So kind of each layer brings a set of new parameters. And when something doesn't go as you expect, it's kind of hard for an end user to start thinking and understanding where my performance issue is coming from. So what I'm saying here is there is still a gap between the metrics that we may have collect from the system in terms of profiling and understanding what the application is doing and actually tuning our application to get the best performance. So what we're trying to solve here is if I have metrics that are being collected on the system, regardless of what kinds of metrics, and we're going to go into more details later on, how can I convert those IO metrics into something that is actually meaningful? How can I understand what is going on with my application based on the data that I have there? And what can I do to make it run faster, run better utilize the resources? So we want to create a tool set that allows us to visualize the characteristics, behaviors, and bottlenecks of our application, detect what are the root causes of the performance inefficiencies, map those into something that is actionable, something that you can do, either you being an end user, an application developer, or a system administrator, to guide you so that we can tune this IO problem. And the way we're thinking about this is towards a kind of a cross-layer IO profiling exploration. As I mentioned, we have all those layers, different metrics being collected at different levels. So how can we integrate everything together? So for that, we kind of created Drishti. And here's a kind of an overall diagram of Drishti. And I'm getting a little bit of a feedback loop. Not sure if it's working okay on your side, but I'll keep going. So for Drishti here, we can think of, we have our own application there running on the system. We have possible different ways of collecting metrics, either through Darshan, which is an IO profiling tool. It can also collect traces to the DXT module, so the Darshan extended tracing. We can have traces coming from custom sources like an HTML5-based trace, and we'll go into a little bit more detail about that later on. We can use Recorder, which is another IO profiling and tracing tool, or P that generates OTF2-like traces. And all we do is kind of combine those information, generating IO analysis of behavior and IO phases, interactive plots so that we can explore what application is doing. So visualize the problem, the issue, the performance issue that we are experiencing, and also providing recommendations and insights. So what is going on with my application? Why is it behaving the way it is? And what can we do to kind of try to fix that? So we're going to go over a couple of things. First, on the analysis part, the visualization part, we do have, this is an example of what we get if we were to take one of those Darshan traces or any other trace, but for this particular example here, it's the Darshan trace of an application. This one handles a lot of HTML5 related files. We just throw it into the tool, into DRHT, and it's going to show us different types of plots there. So operation, transfer size, spatial locality, which is how we access the file, which kind of the offsets through time. Different I/O phases, so when I have read-only phases, right, or a mix in between the two, or something else is going on there, and how I'm using the different OSTs in the system. So all of these plots are interactive, and we have an example right here. Let's see if I can put it. So all of these plots you'll be able to open in the browser. You'll be able to zoom out in particular regions of interest. You're going to be able to put your mouse over any particular dot there and see what are the requests coming from, which is the rank, which is the OST that is the target, when it started, when it ended, what type of operation it is. And you can see it through the different layers. So the MPI/IO layer on top, and that's why you have those kind of big blocks. They represent collective IO operations. And as they percolate down the stack into the POSIX layer, you're going to see that they're kind of broken down into multiple requests. And just from this visualization, you can see that something is kind of strange in a particular, when you have those really huge dots of just one rank doing something. So you can see those tagglers, they're delaying the entire application. Besides you're generating tons of tiny requests, even though you're doing something kind of collective, or what you expect it to be collective behavior through MPI/IO. So it's one step forward where you can visually understand the behavior of your application. But more than that, I mentioned that we want to provide recommendations and insights. So here we have a report that can be used separately. If you don't want the visualization part, you can just get the report on a command line. If you want to use the visualization side, you can get the report as well, combined with that interactive plot underneath it. But the idea here is to provide some insight. For instance, in this application, we have tons of small requests that are affecting the performance of the application. This is what we saw there. We could detect that you could potentially benefit from using asynchronous or non-blocking operations. You're doing a lot of consecutive and sequential requests, which is good. You were using collective operations on the MPI level, so that's good. Overall, we have over 30 triggers, and those 30 triggers are heuristic-based on the literature that we've collected over the last 20 years of IO-related research and things that are considered good practice and bad practice, regardless of the system. So the way that we actually do our IO requests, and this is what we're using this initial version of DRHT to check. It's going to present based on the results based on the severity and the certainty that we have on the impact, depending on the information and metrics we have available, and provide some insight. So what you can actually do in this case, and even provide some sample code snippets when it's needed, or configuration snippet on how you can make some changes to actually try to get around that problem. So with that, that's an initial view of the tool. What we are moving forward now in collaboration with other researchers and some students is trying to drill and go a little bit deeper. So if I have those small requests happening on my application, where is that exactly coming from? Is it coming from actually my code? Is it coming from a transformation as the requests go through the stack? Perhaps, let's say if I'm using an HTML5 application, something that HTML5 is doing that I wasn't expecting, and it's translating into a bad performance, and it's harming my application behavior. So what we try to do here is extend Darshan so that besides collecting all the trace-related information, we can also collect the stack trace related to those issues that I'm seeing. So when I tell you that the application is doing small requests for a particular HTML5 related file, and it's just one rank that is doing that 10% of the small request of the application, and it's coming from line 24 of your own code, then you know that there's where you need to take a look at. That's where you need to either tune something on the way that you're organizing your data or accessing your data, or either activate some of the optimization options particular to the pattern that you're using on your application. So it kind of goes into trying to pinpoint in the code where that issue is coming from. And of course, this is going to work if we have the code available. So that's why we're trying to be very flexible with Drishti in a way that depending on how much information you can present to us, that's how much more information we're going to give you back and be more precise about the recommendations and the insights and where the root causes are. So if you just take a simple Darshan trace with no stack trace information, no trace related data, you're going to get a very simple recommendation and a very simple analysis based on top of your metrics. So besides this is an example that I told you about where it's coming from on the application side and what are kind of the recommended actions for this case. Since we detected that you're using MPIO through HDF5, there are some suggestions that you can change on MPIO related stuff to kind of see if you can optimize your application. So here we have on the two sides here, we have different applications. One at MREX, the other is E3SM with different issues in them. And this is what Drishti is going to tell us. But since we're talking a lot about HDF5, what can we do? Because most of the tools, for instance, Darshan, they don't have a way to collect trace-related information for HDF5 applications. They can collect regular POSIX and MPI calls, but not HDF5-related metrics. On the profiling side, they can do that, but it's a little bit tricky because you have to match the exact version that you're using to compile Darshan to the that you're using to compile your HDF5, so you can actually intercept the calls and get that information, which sounds a little bit complicated, and the problem is already complicating by itself. So what we try to do here is take advantage of one feature of HDF5, which is called the virtual object layer, which is a way that calls kind of go through inside HDF5 and allow you to intercept and do some transformation if needed. In our case, we're not doing transformation. We're just trying to capture the behavior. So what we did here is create a vol connector, like a pass-through vol connector. So it's not changing the way that we actually issue the operations, just something that happens in between, where we get more information about the requests with the focus on HDF5. So we know the context when you're opening a data set, when you're reading or writing an attribute, and we try to get that information and capture the timestamps the exact same way that Darshan extended tracing does, so we can combine information with other sources of data. Essentially, we're collecting this in memory during execution and just dumping events at the end. Here are a couple of operations that we capture from the HDF5 side on the dataset and attributes. Not all of them are of interest for us right now. That's because Darshan, the DXT, the tracing side, only captures reads and writes. So it won't capture open and close related files or file operations for the tracing part. So we're not interested in that, but just on the reads and writes. And the good thing about this is you don't have to actually modify your application. If you have an HDF5 version that supports the vol feature, you just have to have the vol connector installed. You can install it without needing system-wise permission. As a user, you can install it. You set an environment variable that tells HDF5 to use that vol, and you get all the metrics that you want at the end. And what can we do with that is this. We can enhance the same plot that we had before when we showcase. This is a static version, but just for illustrating purposes, we can still have the POSIX, the MPIO layer, but we can now have another visualization on top of that to complement the context and see how things are going on much closer to the application on the high-level library. We can see where the metadata related calls, so the attributes related to HDF5 are happening, both for writes and reads of those attributes. And you can see here in this example, taking a little bit over 3 seconds, we have 3 different phases. You can see we're not using collected because it's the exact same stuff top to bottom. We can see there's a lot of metadata operations that we couldn't understand. They were metadata operations before. And this is what I'm talking about, HDF5 related metadata, not file-wise metadata. But when we use that information and visualize it and go through Bridge to provide a report and act upon those recommendations, in this case, if I recall correctly, they were to use collective operations, flush metadata towards the end, you can get this very well-defined behavior that we have on the right side and reduce the application execution to less than 1 second. And you can see that now we're using collective properly because on the POSIX level, we just have a couple of aggregators that are actually doing the IO request. And we have the very well-defined phases of the application, including the metadata towards the end. So we don't have those kind of chopped behavior that we saw before. So this is the way that you can get more information about HTML5-related application. And I just want to share a couple of other 2 features that we're working on to enhance this Bridge umbrella. One of them is, so far we've discussed using Bridge as an end-user application developer to get more insight on the code that I have, but I can also use Bridge system-wide to get some insights on what are the common issues that either my project or my user base is suffering from. So what we do here is use the same triggers, same insights we have on Bridge, apply it system-wide daily, and you can get, hey, yes.
Can you wrap it up quick here, because we're kind of running out of time here. You're actually a little
absolutely,
bit over your time.
Absolutely.
Yep.
Just 2 more seconds, I can finish. So you can get this insights. This is an example we got from traces on an Earth machine over 1 month, so you can see the most common issues happening there. And to finalize, I just want to kind of showcase something new that we're working on right now. I hope this loads. If it doesn't, you have to trust me. Well, it's a way to use large language models to explore those traces and metrics so that you can get more information and interact with it, trying to understand what's going on. So it's a little bit more interactive and user-friendly than a regular report. So summarizing, that's what we're trying to do with Bridge: detect root causes, map them to problems, recommend actions based on heuristics initially, but going to more complex triggers. And this is what I want to share with you. If you have any questions, we have our code available on GitHub. Be happy to answer them now, or if you want to reach out and connect later on, please do. And thank you. There are, because I mean, due to the complexity of the applications, the way that we interface with the IO stack and different characteristics of the systems, sometimes there are things that are very particular to one system, to give an application, and trying to provide like an overall view as we do this with Bridge is kind of like a really hard limit, and we don't want to kind of be very, very specific, but rather provide some initial guidelines and insights. We don't claim to solve the entire problem, but we're just hoping to get users, sysadmins, and developers to kickstart fixing their IO-related issues.
So I'm from Lawrence Livermore. I'm Hari. I'm a computer scientist at Lawrence Livermore, and this work we've been looking at explainable IO. So there's a lot of echo. I can't even. I'm hearing myself right away. It's hard to talk. Hello. Okay, let's see. This is better. So we are looking at explainable IO. Basically, we are looking at our current tools and trying to see if we could, instead of saying what is happening within our system, look at IO performance, but can we explain why it is happening, essentially, by looking at multiple layers and trying to look at the stack rather than just the result of that stack. So this work has been, we've been looking at it for the past 6 months with Sarah Neuwirth from Germany and Jay Lafstead. Let's see. Okay. So as Gianluca kind of talked about this briefly, I kind of skip over in the interest of time, is our current HPC infrastructures for IO are extremely complex. We have from new computational paradigms, from AI machine learning apps at the top, with more complex workflows working together. And so we have to also look at how's the data flows between the applications, between different architectural, from heterogeneous solutions to our classical homogeneous solutions to tiered storage. So there is a lot of heterogeneity everywhere, which needs to be dealt with from a user perspective when they're trying to optimize data management for their applications. On top of that, we are looking at new operational paradigms where we are starting to converge more closely with cloud solutions for some highly specialized jobs. In close coupling with HPC systems, which further makes a lot of our tooling and infrastructure extremely hard. And typically, for humans to adapt to this automatically and detect issues, it's very hard. And so the general premise of this work, um, in general, we depend from a user perspective and from a facility perspective. No matter how big or small your cluster is, we depend on a lot of monitoring infrastructure to understand our performance data for IO. Typically, you want, in an ideal world, you want to be able to get insights on how your application is performing. That's the what, and that's kind of what nicely Gianluca's Drishti does, and which is very useful for users to understand what's happening. But on top of that, you want to have a little bit more visibility into why that is happening, and basically put that in a feedback loop for the users and for the system admins in order to procure better systems for their applications for the future, or optimize their, or for the users, optimize their workloads for that particular system, to actually do something which is both better in terms of utilization of the system, which in turn helps their application. So at the end of the day, that's what we want to achieve from both these sides, the users as well as the facilities. I kind of call it the tracking the data trail, because essentially we have to understand how the data is flowing in the system. And this is an interesting example, which also Gianluca kind of the previous presentation talked about briefly, where you have an application which could be using a high-level library like HDF5 on top, and then going through the stack of MPIO, POSIX.io, and really low-level file system calls, and then storing all that information into Darshan logs. A lot of today's machines store these logs as profile logs, so you have high-level aggregated metrics. But as we talked with some of the community people who are using these logs, some main questions which come is, because the way these logs are eventually exposed to the users or the other research community, typically after a machine goes away for people outside, that's when the logs are made public in most cases. If you're working at a facility, sure, you might get a little bit more information, but typically that's for a shorter period of time, and you cannot really continue to use that for research on a long-term basis. Most of our long-term, like 3-year logs or 4-year logs from Argonne, from Theta, and everything comes from really, really from machines which have been out of commission and not on provision. So the question basically comes as how current they are for our current systems that we are looking at today. Another question which often comes up in a lot of these studies, which is kind of unknown still, is the completeness or the integrity of these logs. We have little to no information sometimes, not everywhere. In some cases we do, but not a lot of studies look at whether my data set that I'm collecting from Darshan is complete. And we talked about this in the community. A lot of facilities. One of the things they talk about is sometimes when if a workload or a science application which is running on large scale has an issue and they see some profiling tool like Darshan turned on, they typically turn it off as the first thing to do, whether Darshan was the problem or not, and which is in general not a good sign for these kinds of studies. On top of that, just looking at what happened, that is, oh, I spent X amount of time on read operations and X amount of time on write operation, can tell you what your application did on the system, but does not really tell you why. And that's kind of the main challenge in these things. So from a very high level perspective, the key goals initially when we look at explainable IO, we were thinking about what is our current HPC compute and storage ecosystems look like. In this, we have to think about not just the tier 0 and tier 1 systems like supercomputers deployed around the globe, but also tier 3 systems like smaller clusters in these supercomputing sites or in cluster in the labs or cloud-like infrastructures like Chameleon. So you have to look at all these kinds of different paths because all these might have different storage hierarchies and you have to think about different kinds of data paths that might exist. And then we also need to kind of think about, is Darshan is the only one out there, or is there a difference based on different monitoring tool in different kind of regions of the world? And as we're looking at this, I think there is in US Darshan seems to be the prevalent one, but in Europe there are other like Pika, Scarpi, which are more prevalent on these clusters. So how does this diversifying monitoring infrastructure work? There was a great study last year at Cluster where it was shown that different tools kind of measure things differently. They measure different things. How do we use this kind of diverse monitoring infrastructure from different places to our benefit? And then finally, kind of thinking about if you really think about modern infrastructure with a lot of heterogeneous IO and storage architectures, a lot of middleware library solutions like PTC, UniFiFS, Hermes, then you have to also think about how well these monitoring infrastructure are capable of supporting these new software and hardware challenges. Um, from this, we kind of started to look at the community first and see and look at some of the top lists that we have, which kind of talk about both the compute and the storage. Some of these lists focus purely on compute, others purely on IO. The reason we look at both is because we also want to, as we said, look at the coverage of these lists. If we just look at IO in an isolation, then we might be biased about the types of systems we have, and we might not look at the coverage as well. So we wanted to look at these four well-known lists in the community: the top 500, the Green 500, the IO 500, and Virtual Institute of IO has a list called Comprehensive Data Center List. And all these have a lot of interesting information in terms of what kind of a system it is, what's the ranking, and everything. And at the same time, some very IO driven lists or storage driven lists like IO 500 and the Comprehensive Data Center List have a lot of storage related information for some of the systems. So that kind of we hoped initially to look at these lists and try to understand what's happening. This is just one of the results we initially found from IO 500 that we looked at what are the types of systems we see there from a high level. In general, it had about 1% of the top 500 machines there, which in itself is not a great sign because only a handful of them, like Aurora or one from Europe, was there, which was out of the hundreds of systems that were there. There were a lot of test clusters from theirs. There were a lot of generic file systems like Lustre. But also there were some weird entries of file systems like parallel file system and SSD as I say here. So this is not to say that the list is not useful, but I think somewhere the completeness of the list needs to be thought about, and we probably require again some form of validation of how we can map our top 500 systems into this list better. In terms of when we look at this and including the comprehensive data center list, at the end result was we were looking, as I said, into the different data paths that could exist, and we built this kind of a higher level diagram of the different kinds of data paths we have to think about from a computing element standpoint, because we move a lot of data between CPUs, GPUs, DPUs, and all in between, we have to think about data elements or data paths between them. Then we have a bunch of storage tiers, like node local best buffers or shared best buffers, tapes, data lakes, parallel systems, and all of them have typically either a homogeneous link to the compute nodes or a heterogeneous link depending upon the architecture or how far back you go. They have a little bit different. So you have to think about some are connected by Ethernet, some are connected by Infinity Band, some are connected by PCIe or over NVMe over Fabric. So you have to think about how these work. And some we don't even have that information out there, that how are they even connected when you have a distributed tape all over the place. In other places, also you have to think about what type of storage we have. We move from traditional SATA SSDs to RAID SSDs to today a lot of the clusters have NVMe deployed close to the compute, and even NVRAM in certain cases. So we have to think about how are these changing our performance, and if a read was taking X time from Darshan, how is that going to change if we change any of these data paths, if we change the tiers, if we change the storage, if we change the computing element. And that's kind of is the overarching goal of this project, is to try and understand when we do IO operations, why does it give the time that it is giving. From a very the dashes are all over the place here it's okay. So when you think about what kind of information we are looking at, we today only cover a very few paths of the overall system, and I was trying to highlight the PCIe and the PCIe over Fabric there, or the net or the connection to it. So for instance, if you're looking at Darshan, Recorder, Defacer, all of them are user space libraries which are going to say, oh, this is the IO you did, and it will time it and give you the information. That really does not translate to whether this went out of the node, whether it touched the local NVMe, or it went to the parallel system, it went to the remote nodes NVMe. So you have to think about not just what it the capture we are doing are such at a high level that we can only say what happened. We can't really say why that IO call happened. And with more complex softwares we are building to help the users, this becomes more almost useless, because the same IO operations have a lot of variability from all the way from memory performance to an hard drive performance. So it's very hard to understand where the cost is coming from sometimes. And so you have to, when you think about this problem, you have to think about multiple software stacks. So as Gianluca talked about, HDF5, MPIO, POSIX, but also you have to think about what stack in the kernel is it after the virtual file system layer, is it directly going to the other node, or is it going through the stack and going down to the local NVMe, or it is not even going to the virtual file system, directly going to a parallel system client and from there. So there are so many these data paths exist that it is very hard to understand what's happening there. And finally, use all these pieces of data movement through the kernel stack, through the remote node, and through the file system to kind of stitch up what is happening for the application. So so we build this data crumbs tool. We are starting to build this prototype and look at how this would work. This tool uses ePPF. It's not open source yet, but this is kind of our initial effort to try to look at this multi-stack. And I have some very quick kind of initial results to demonstrate here. So you can see here essentially a difference between F read call and a read call. And when you do typically an STTIO F read call, you can in Darshan, you can actually not know that both are happening, right? Underneath, F read is going to call read, but you don't really see that on the system call level. You really see what libc is showing you. And so because of that, you miss information like F read breaks things into smaller reads, and there is the notion of its own buffering. So some of this buffering stack that you would see on a normal system call read call goes away. And so those kinds of information are missing, which ends up making IO more opaque. So you're thinking about what kind of different buffering layers are involved, what kind of structures in the kernel are buffered, which are required for understanding what would be our read cost in the future. So are the inode buffered? Are the PIO layer buffering the page cache? Are you having before the PIO layer the page cache involved? So you have to understand all that part in order to say what is the cost of my F read or a read. So in this talk, I kind of tried to motivate some of our initial efforts, and we are looking more for feedback from the community of what they think of the overall thought process of our current monitoring tool. I hope I kind of showed that we have a lot of data paths and we don't have a lot of visibility into them, and so we have to look at tools which are beyond user space to help see the IO behaviors. And I tried kind of show and motivate some of the initial results we had with data crumbs really quickly, because there was not a lot of time. I couldn't go into detail, but I can take any questions if there are any. At the last thing, I want to just talk about where is this useful, right? So if we have better visibility and we can explain IO from our monitoring tools, then we can actually do performance modeling. Today, we do a lot of hit and miss in terms of performance modeling. We throw AI into it, but I don't think we have enough data for even AI to figure out what is there. We only know what happens. Another hard thing to do is performance debugging, right? So as Gianluca alluded many times, it is required for people to know where to go and look for problems and how to fix them. And to do all that, you need better visibility on your stack of how you're doing this. And look at more multi-component instead of looking at IO in isolation. Look at GPU kernels and IO together, and all these kinds of characterization require more data, I think, from our tools. And so that's where I think the main direction of this work is going to go by. With that, I'll stop here and take any questions if there are any. Thank you for listening. Yeah. So think of it this way, right? So currently, Gianluca's work, I don't know if you can see my slides. Can you?
Not yet.
Oh, not yet. So,
No.
So in my example that I was trying to demonstrate with F read versus read, right? So Gianluca's work with Trishti can nicely tell you which of the F reads are problematic. Okay. But they cannot, but because Darshan does not give you further lower level information, they cannot say why is it a problem. They can, based on our experience of HPC, we can guess, but it's an educated guess at the end of the day. You see what I'm saying? So if you, let me take an example of it, right? So when we do F reads, if we do 4 kilobyte reads, on a parallel file system, that's a worse thing to do than on a local NVMe. Mm-hmm. It's not always a problem. It's relative to what happened within your software stack. And there are buffering solutions like Hermes, PDC, UniFiFS, which can take those 4 kilobyte reads and just buffer it in memory. So you won't even see it touching the file system as a 4 kilobyte.
I see.
Read or write, which basically tells you that you need visibility into what happened within your stack first in order to go and explain it in back. But because we don't have that, I think Gianluca's approach is what we have today. Does it make sense?
Yes, yes.
So the goal here is that if we are able to expand the amount of information, then tools like Drishti or the LLVM based tool, it's not LLVM, LLM based tool he could not show, but I have seen that in the past, could do is actually figure out what was the cause of it, rather than saying this is problematic and this is not, kind of saying why it is. I think that's the main part that today tools are not giving us in order to build better Drishti tool in that sense.
So say why we have a problem, not the. Okay. Okay. Thank
Yeah,
you.
that's the idea, right? So
Mhm.
you're trying to say you're trying to say there are two reads. One hits the OS cache and one does not. Typically, we guess that this hit the OS cache and this does not because we don't have the counters.
Okay.
So these kinds of problems are basically for us to figure out the why of an IO operation rather than saying what happened.
Yes.
So that's why it's complementing that way.
Okay. Thank
Hopefully,
you very much.
All right, let's thank our speaker.
okay.
All right, thank
Thank
you.
you.
All right. And this concludes this session.